Okay, let's look at the worksheets for Chapter 5 and Chapter 6. Now, not going to do all the problems, and we're just going to try to hit the main points in this. This is to supplement what we've done in class, and let's see how this goes. Now, we want to mark the multiples of pi over 6, pi over 4, pi over 3, and pi over 2 on this unit circle. And I'm assuming that you've looked at the little preview video or the summary of trig, and that we know that the sine of pi over 4 is the same as the cosine of pi over 4, square root of 2 over 2, and the sine of pi over 6 is 1/2 cosine of pi over 6, square root of 3 over 2, and that is equal to the cosine of pi thirds and the sine of pi thirds. And we went over that in the little summary video. So we're assuming this is a unit circle, 1, 0, 0, 1, minus 1, 0, and 0, minus 1. And no matter how many times you go around the circle, if you end up here, if this is the terminal point of your angle, then this is a multiple of 2 pi, 0, 2 pi, 4 pi, 6 pi. The coefficient of pi is even, and then over here the coefficient of pi is odd. Now, let's do some things here that are kind of fun. If you look up here, the sine of pi over 6 is 1/2. Well, the sine is a y value. So if I go here, if this is 1, and I guess where 1/2 is, and I now take my ruler and try to place it so that it's parallel to the x-axis, that's pretty good, then that's going to give me, if I connect it with the origin like this, that's going to give me where pi over 6 is, because the sine of pi over 6 is 1/2. And remember, the sine is a y value. So this y value, this perpendicular distance, is 1/2, if that's 1. Now, I can do the same thing over here. I'm just showing you how you can do this very quickly, just using what we've observed here. So see, I have got the multiples now of pi over 6. So this is pi over 6. This is pi, which is what? Pi would be 6 pi over 6, so this has to be 5 pi over 6. This is pi, 6 pi over 6, so this has to be 7 pi over 6. All the way around is 2 pi, which is 12 pi over 6, so this is 11 pi over 6. Okay, now for pi over 3, remember that the cosine of pi over 3 is 1/2, and the cosine is an x value. So I'm going to try to go and guess, that looks to me to be about 1/2. And I'm going to draw, or try to place my ruler parallel to the y-axis. And that looks pretty good. So I'm going to come up here and draw an intersection. And then that's going to form, when I connect it through the origin best I can, that's going to give me the angle of pi over 3. Okay, so that's going to be pi over 3 radians. Now this is pi, which is 3 pi over 3, so this has to be one more, which is 4 pi over 3. Now, this is 2 pi, which is 6 pi over 3, so this is going to have to be 5 pi over 3 when I connect it. So let's do that. As best that I can. So I've got my 5 pi over 3. Now this is pi, which is 3 pi over 3, so this has to be 2 pi over 3. Isn't that cool? Very, very simple. Now, what about pi over 4? Well, if we think in terms of degrees, pi over 6 is 30. And pi over 3 is 60. So I want to try as best I can to split the difference here. Because this is 30, this is 60, 30, 60. That's a difference of 30 degrees if you want to think in terms of 30 degrees. So if I'm at 30 and I want to get to 45, I just add 15, which is splitting this. So I'm just going to make my best guess, something like that. I don't have a protractor, which is what you would need. So I'm going to draw this like this. And that's going to give me then pi over 4. Now this is pi, which is 4 pi over 4, so this has to be 5 pi over 4. And I'm going to try to do the same thing right here. Let's split the difference right there. Connect that to the origin as best I can. That looks pretty good right there. So this is pi, which is 4 pi over 4. If I back up 1, I get to 3 pi over 4. And now this one down here, this is 2 pi, which is 8 pi over 4. Back up 1, this is 7 pi over 4. So that's an easy way to do that. That's kind of a fun way to do it. And it's not extremely accurate. In fact, it's pretty inaccurate. Now, we want to label them with the terminal points. In other words, what's the coordinate here? Well, this is pi over 6. This distance is pi over 6. So all the way around would be 2 pi units, a little over 6. So this is going to be about what? If all the way around is 2 pi, this is going to be about what? Well, about 30 degrees, or about 1/12 of it. Okay, but the coordinate's easy enough. The sine of pi over 6 is 1/2. And the cosine is the square root of 3 over 2. Pi over 4, it's the easiest one on the page. Square root of 2 over 2. Square root of 2 over 2. Pi over 3, well, the cosine of pi over 3 is 1/2. The cosine is an x value. And the sine of pi over 3 is the square root of 3 over 2. Now imagine folding this piece of paper along that line that's pi over 4. This point would be reflected right here. And of course, when we fold and when we reflect, the x and y values change. So remember this one. And what I do is I remember this one. And I can get everything else for these guys just by doing that. Of course, I know pi over 2, 0, 1. 3 pi over 2, this is 3 pi over 2. This is pi over 2. This is going to be pi, 3 pi, 5 pi, 7 pi, etc. Now, 2 pi over 3. The coordinate here is going to be exactly what the coordinate for pi over 3 is, except in quadrant 2, x's are negative and y's are positive. So this is going to be a minus 1/2, and it's positive square root of 3 over 2. And the same thing goes here. This is going to be minus square root of 2 over 2, square root of 2 over 2. Pi over 6, pi over 6. Oh, look at what I've done. I've got that one wrong. Do y'all see that? That one is wrong, isn't it? That's pi over 6. The cosine of pi over 6 is square root of 3 over 2. Sine is 1/2. And then when we fold it, yep, I messed up. Now 5 pi over 6 is going to be the same thing as pi over 6, except this is negative. And the y value doesn't change. 7 pi over 6, the numbers are going to be the same as for pi over 6, except in this quadrant, both ordinates are negative. So it's a negative square root of 3 over 2 and a negative 1/2. 5 pi over 4 minus square root of 2 over 2. Square root of 2 over 2, negative. 4 pi over 3, it's going to be a minus 1/2 and a minus square root of 3 over 2. Now, 5 pi over 3, in this quadrant, x is positive and y is negative. So 5 pi over 3, the coordinate's going to be the same as pi over 3. It's going to be plus 1/2 and minus square root of 3 over 2. 7 pi over 4, square root of 2 over 2, minus square root of 2 over 2. And finally, 11 pi over 6 is going to be square root of 3 over 2 and negative 1/2. And that is section 5.1. So that's a fun way to do it, just using this information. Okay, now let's look at section 5.2. We have to fill in this table, and using what we know, let's write what we know again up here. Let's write what we know again. We know the sine of pi over 6 is 1/2. Cosine of pi over 6, square root of 3 over 2. Sine of pi over 4, square root of 2 over 2. Cosine of pi over 4, square root of 2 over 2. Sine of pi over 3, square root of 3 over 2. Cosine pi over 3, 1/2. Okay, let's fill out our table. Now, what I'm going to do is refer back. I'm going to refer back to what we did in 5.1. Okay? So I've got this all filled out for 5.1. And I'm going to draw me a little unit circle right here to begin. So at 0, the sine is 0, cosine is 1. Now tangent sine over cosine. So it's the y value over the x value. So it's 0 over 1, which is 0. Cotangent is going to be the x value over the y value, or the reciprocal of tangent. So that does not exist. Cosecant is 1 over the sine. That does not exist because the sine is 0. And the secant is going to be 1 over cosine, which is 1. Okay? It's that simple. Now, pi over 6, we know, is 1/2. Cosine square root of 3 over 2. Now, I like to do things this way because now when I want the tangent, I just draw a line here and make this a fraction because tangent sine over cosine. So it's going to be 1/2 divided by the square root of 3 over 2. So it's 1/2 times 2 over the square root of 3, 1 over the square root of 3, or square root of 3 over 3. So this is square root of 3 over 3. The cotangent's the reciprocal of this. Well, that's 1 over the square root of 3, and then we rationalized it. So the reciprocal of 1 over the square root of 3 is square root of 3. Cosecant is 1 over sine. 1 divided by 1/2, 2. Secant is 1 over cosine of pi over 6. So that's going to be 2 over the square root of 3. It's going to be 2 divided by square root of 3. So that would be what? 2, it's 2 divided by square root of 3. And then when we rationalize, we get 2 square root of 3 over 3. Now, pi thirds, it's real easy. I'm going to take the cosine from pi over 6 and write here. Okay? So for the sine of pi over 3, I'm going to take that cosine and write right here. For the cosine of pi over 3, I'm going to put this here. Now, for the tangent of pi over 3, I'm going to put the cotangent of pi over 6. For the cotangent of pi over 3, I'm going to put the tangent of pi over 6. They're co-functions. So now, what's going to be the cosecant? Well, it's 1 over the sine, or it's simply going to be this. So it's 2 square root of 3 over 3. And finally, the secant of pi over 3 is going to be 2. Now, notice that pi over 3 is listed twice. Let's make this one pi over 4. Okay. So square root of 2 over 2, square root of 2 over 2. Now look at the tangent. Take this fraction. So I got square root of 2 over 2 divided by square root of 2 over 2 is just 1. Cotangent's the reciprocal of tangent, which is 1. The cosecant's 1 over the sine. So that's going to be 1 over the square root of 2, or just the square root of 2. Sorry about that. And this will be 1 over the square root of 2, square root of 2. Now pi over 2. Pi over 2 is right here. Its coordinate is 0, 1. So the sine is 1. The cosine is 0. Now tangent sine over cosine. So this does not exist. Cotangent is cosine divided by sine. 0. Cosecant's 1 over sine, 1. Secant is 1 over cosine, so this does not exist. Okay, pi, this is minus 1 and 0. So the sine is 0, the cosine is minus 1. Tangent sine divided by cosine is 0. Cotangent's the reciprocal of tangent, so that does not exist. Cosecant's 1 over sine, that does not exist. And secant is 1 over cosine, so it's minus 1. Now 3 pi over 2 is down here. Cosine is minus 1. Sine is 0. Tangent is sine over cosine. That does not exist. Cotangent would be 0 divided by minus 1, so it's 0. Cosecant's 1 over sine, so it's minus 1. Secant is 1 over cosine. Does not exist. 2 pi is back where we started, so you would just copy these values down again. Now let's have some fun. Sine of 5 pi. Well, remember, this is pi. 3 pi, 5 pi, 7 pi, 11 pi. So the sine is that y value, so that's 0. Now sine of 5 pi over 2. Now here's how you do this. This is pi, which is what? 2 pi over 2. This is 2 pi. 2 pi is 2 pi. 2 pi is 4 pi over 2. So we need to go one more, don't we? So it's right here. So the sine of 5 pi over 2 is going to be that y value, 1. Cosine of 7 pi over 3. Well, here's 2 pi. 2 pi is 6 pi over 3. So I need to go one more. So 7 pi over 3 is right here. So the cosine of 7 pi over 3 is just the cosine of pi over 3, which is 1/2. Now, it's really not right there. It's more like this, but it's in quadrant 1. That's all I care about. Cosine of 99 pi. 99 pi is right there. The cosine is the x value. That's minus 1. Tangent of 5 pi over 4. Here's pi, which is 4 pi over 4. So 5 pi over 4 is in this quadrant. So in this quadrant, both x and y are negative. And so it's going to be this. Remember, the tangent of pi over 4 is this over this, so it's 1. In this quadrant, both x and y are negative, so it's the y value over the x value. So it's still going to be plus 1 since they're both negative. Now cotangent of minus 2 pi over 3. So here's minus pi, which is minus 3 pi over 3. So it's here. It's in this quadrant. So I'm looking for the cotangent. So it's going to be the cosine. See, the cotangent of negative 2 pi over 3 is going to be the cotangent of pi over 3. Okay, so what's the cotangent of pi over 3? The cotangent. So it's going to be the cosine over the sine. Now they're both negative since it's in quadrant 3. So this is going to be minus 1/2 times minus 2 over the square root of 3. So that's going to be a 1 over the square root of 3, or a square root of 3 over 3. Secant of 6 pi. Well, 6 pi is right here. Secant is 1 over cosine, so this is just 1. And finally, the cosecant of minus 13 pi over 6. Well, this is minus 2 pi. Minus 2 pi is going to be minus 12 pi over 6. So we have to go one more. So it's going to be in this quadrant. So the cosecant of minus 13 pi over 6 will be the cosecant of pi over 6. Pi over 6 is the reference angle. Now it could be plus or minus. Well, the cosecant of pi over 6, cosecant is 1 over sine, so it's going to be a 2. And in quadrant 4, the y values are negative, so the cosecant is going to be negative, so it's going to be a minus 2. Okay, let's look at the second page. I wanted to do all of that page. It's really simple, folks. Once you get just a couple of things under your belt, all you're doing is going around in circles, and you're using the fact that each quadrant contains one and only one multiple of pi over 6, pi over 4, and pi over 3. That's the secret to this. Let's look at the second page real quick. Now, it says use a table of values to graph the sine function. Well, let's make sure we understand what we're doing. If we look at the unit circle, as we let the angle go from 0 to pi over 2, what we're doing is we're plotting these y values. That's all we're doing, is we're plotting y values. So the sine function is periodic. You get one complete sine curve over every interval that's 2 pi units long. So here's 2 pi on the scale. This is going to be my t-axis. This is the y-axis. And I'm plotting y values. I'm just plotting the y values. So I'm going to mark halfway here as pi. Halfway of that is pi over 2. Halfway of this is 3 pi over 2. So let's plot the y values. When t is 0, I get 0. At pi over 2, the y value is plus 1. So let's say that that's 1, and let's say that this is minus 1. So I'm at this point here. If I go around to pi, the y value is 0. If I go to 3 pi over 2, the y value is minus 1. And then if I go to 2 pi, I'm back to 0. And I'm just sketching the y values. So it has this form right there. Of course, now it continues back this way. And it goes on forever. But there's one complete sine wave over one period. So the domain, well, the domain can be anything. Or, see, I don't know how to answer this. The domain of sine t can be anything. So I'm going to put that, even though I just plotted one part. And see, it keeps going forever this way. The range, I get y values from minus 1 to plus 1. And the sine function is an odd function. All the trig functions are odd except for cosine t and secant of t. These two are even. The others are odd. Now that means it is symmetric about the origin. And remember, if I come here and draw a line through the origin and extend it, I get another point. If I draw a line through the origin, I'll get another point like this. The cosine and the secant are even functions, so they're symmetric with respect to the y-axis. Okay? I'll let you do the cosine, and all you're going to do in the cosine is plot these x values. Okay? Now the tangent's a funny one. Because see, tangent is sine t over cosine t, right? So it's the y values divided by the x values. Well, look, at 0, you have 0 divided by 1. So the tangent is 0. And then look at pi over 2. you have the y is plus 1, and the cosine, the sine is plus 1, and the cosine is 0, so it's undefined. See, this thing is undefined at pi over 2. Now, if we go this way, we go negative, it's undefined at minus pi over 2. Okay, so the graph would look like this. Because, see, just look at your x value. As the angle of measurement gets closer and closer to pi over 2, the x's, the denominator, cosine, gets closer and closer to 0, so it goes to plus infinity. And then what happens is we come over here and we get infinitely many branches. This would be 3 pi over 2. Here's pi. And you get infinitely many identical branches. So the domain, this is hard to write down because the domain is going to be pi over 2 plus or minus then some multiple of pi where n is equal to 0, plus or minus 1, plus or minus 2, etc. So if I start at pi over 2 and add pi units I get here, if I start at pi over 2 and let n be minus 1, I get this one. So the range would be all real numbers from plus infinity to minus, and the tangent is an odd function. Okay, that is it for section 5.2. Let's look at 5.3. All right, let's take a look at sections 5.3 and 5.4 on these little worksheets. So it says you're given the graph of some function. List the period, amplitude, and phase shift, and write the equation of the function. Now let's look at this thing. Let's look at it. It's repeating over an interval. So it's a sine, or it could be a cosine. So let's first talk about the amplitude. The amplitude begins at minus 2 and plus 2. See, the low point is minus 2, and the high point looks like it's plus 2. So the amplitude is going to be 2. Remember, the amplitude is the absolute value of what you see. We see a low point of minus 2, a high point of plus 2. So it's going to vary from 0 to 2 and 0 to minus 2. So the amplitude is 2. Well, now, what about the period? Well, let's look. It's hard to see because my sheet's pretty blurry. This looks like it's in increments of pi. So I'm going to go from this high point to that high point. Okay? So it looks like it's going to go from minus 3 pi to plus 3 pi. So the period, if we go and subtract the big number, which is 3 pi, minus a minus 3 pi, so we get the period as 6 pi. So if we look at this high point here, I'm going to get one complete curve, or back to the next high point, over an interval of 6 pi units. And I got 6 pi by taking the value on the right minus the value on the left. Okay, now phase shift. Phase shift. If I shift this to the right, if I shift that high point to the right, a distance of 3 pi units, 1, 2, 3, I get this curve right here, and what it would be a cosine curve. So I'm going to say the cosine, I'm going to say it's going to be a cosine curve shifted 3 units to the left. So that's going to be a phase shift of what? Minus 3 pi. So now I think it's a cosine. So this cosine has been shifted left and right and stretched. So remember, the generic equation is absolute value of the amplitude, cosine. Now the period is 6 pi. And remember, the period is going to be 2 pi over k. And we want that to be equal to 6 pi. So if I cross multiply, I get 2 pi is equal to 6 pi k. So k is equal to 1/3. So this is going to be 1/3. And then it's going to be x shifted to the right 3 pi. So I've built me a cosine function. So this a, if we put a 3 there, that means if I shift this over, the high point should be 3, and it is. So I'm going to put a 3. So my equation is y is equal to 3 cosine of 1/3 times x plus 3 pi. Okay, cool. The functions tangent and cotangent have a period of pi units. Okay, the functions secant and cosecant have period, 2 pi. There are 6 trig functions. Tangent and cotangent have periods of pi units. Everything else has a period of 2 pi units. So sketch the graph of these. We'll do some of these. I'm going to declare that to be pi over 2. And I'm going to declare this to be minus pi over 2. So what I'm going to do is draw one branch of it. Okay, and it just repeats. If we extend this and come over here to 3 pi over 2, halfway between them is pi, and you would get another branch. Now cotangent, remember cotangent is cosine x over sine x. So the sine is 0. The sine is 0 at what? Pi. Okay. And 0. So it's going to go, here's pi over 2. It's going to go like this. Remember, it's a backwards S. This is kind of a lazy S, and this is kind of a backwards S. And so if we come over here to minus pi, and this would be minus pi over 2, we get another branch like that. Okay, secant. This is how I remember the secant. Secant, remember, is 1 over cosine. So what I'm going to do is sketch in a little cosine curve here. See, and it just keeps going. If I want to draw it out like this, it keeps going this way too. It's going to go right through 1, come down here, come up, like so. See, I'm drawing in the cosine curve. Well, now the cosine is 0 is at pi over 2. So this would be 1 over 0. So this is undefined at pi over 2. That's a fence. It's a vertical asymptote. This is minus pi over 2. And then I just come up here and see how these legs turn down? Well, what's the reciprocal of, or the opposite of turning down? Well, they turn up. Then at 3 pi over 2, and these turn up, so the opposite or the inverse would be turning down. And see, I get, this is one complete secant curve, the upper branch and the lower branch. That's one complete cycle of the secant curve, and it takes place over an interval of 2 pi units. Cosecant is 1 over the sine function. So if we just sketch in a little sine curve, and see, the sine is 0 at pi, so I'm going to put pi here. That's a vertical asymptote. Here's 2 pi. 0, the sine of 0 is 0, so this will be a vertical asymptote like that. Here's minus pi. And remember, all we do is draw the opposite now. That turns up, that little that little part turns up, so this will turn down. This turns down, so that will turn up. But if we look over any interval that contains an upturn and a downturn, it's going to be over an interval of 2 pi units. Okay, let's look at page 2 of 5.3 and what we got here at 5.4. Okay, now 5 cosecant is going to be exactly this curve. Let me get this back up here. 5 cosecant is going to be exactly this curve, but instead of it being at 1 and minus 1, this will be shifted up to 5 and minus 5. So this low point will now be up here at 5, and it'll be like that. Okay? So it's just like the cosecant curve, except it's been shifted. Now this is the tangent of x plus pi over 4. Now here's a way to do this. Here's a way to do this. If you take this argument, here's one way to do this. We know the tangent has got vertical boundary lines at pi over 2 and minus pi over 2, right? So I'm going to take that argument. I'm going to take x plus pi over 4 and set equal to that fence, equal to pi over 2. So x would equal pi over 2 minus pi over 4, which guess what is pi over 4. So see, now I'm going to have a fence right here. Okay? Now take this argument, x plus pi over 4, and set it equal to minus pi over 2. So x would equal minus pi over 2 minus pi over 4. Well, pi over 2 is 2 pi over 4, so this is going to be minus 3 pi over 4. So what happens is this gets shifted pi over 4 units to the left, which is what we know, and this gets shifted pi over 4 units to the left. So halfway in between is going to cross the axis. Now, what would be halfway? Well, it's pretty easy, isn't it, folks? In the reference curve, the tangent of x goes through the origin. So this is going to be shifted pi over 4 units to the left. So this is at minus pi over 4. So it's just the regular tangent curve shifted pi over 4 units to the left. Pretty easy. Let's do the secant of pi x. Now, what I want to do, remember secant's 1 over cosine, so I need the cosine. So I'm going to sketch in the cosine. But this is kind of funny, isn't it? Well, let's just look at it. Now, the secant, the normal secant function is undefined at pi over 2, right? It's undefined at pi over 2. It's undefined at 3 pi over 2. Because remember, secant is 1 over cosine, and the cosine of pi over 2 is 0. Wherever, I didn't draw that very well, did I? Wherever the cosine curve touches the x-axis, the secant will be undefined. So it's going to be undefined here at minus pi over 2. So what I'm going to do is take this argument, pi x, and set equal to pi over 2. And I'm going to solve for x. So I get x is 1/2. Now, pi over 2, pi is about 3. 3 divided by 2, this is about 1.5 numerically. So this boundary line is going to be shifted to 1/2. This is going to now be 1/2. Okay, and I'm going to do the same thing to this one, to minus pi over 2. I'm going to take pi x and set equal to minus pi over 2 and get x as minus 1/2. So it's going to be like this. So that means the normal curve is going to be like this. The sine of pi over x will be like that. Now we can continue this. We can take pi x and set equal to 3 pi over 2. Cancel the pi's and we get x is equal to 1.5. So this is 1/2. This would be 1, so 1.5. So that means down here at -1, right halfway in between them, down here at -1, I'm going to get this. So I have fences. I have fences at -1/2 and +1/2. That's a total distance of 1, isn't it? And then I go from 1/2 to 1.5. That's a distance of 1. So this is going to be the normal secant function, except it's squeezed together. And remember, the period is 2 pi over k, and k is pi in this problem. That's a k. So the period is 2. So I get one complete secant curve over that interval. Now, section 5.5 is dealing with inverse trig functions. So now let's talk about this. If we look at the inverse sine of x. So if I said y equals inverse sine of x, now again, this is kind of like a logarithm. The notation is not good. This is not the reciprocal. So if I take the sine of both sides, I get the sine of y equals x. So this notation means this. Remember this, inverse trig functions are angles. That's what an inverse trig function is. Now let's do the little history here. If I sketch out the graph of the sine function, see, this would be 2 pi, this would be pi, pi over 2 minus pi over 2, etc. This would be 1 minus 1. If we draw a horizontal line in here, we cut the curve in more than one place. It is not 1-to-1. So that means it does not have an inverse. So what we do is we restrict the domain. We're going to only look at the part of the curve right here. So for y equals sine x, we're only going to use the x's between minus pi over 2 and pi over 2. And that is going to give us just the y values between 1 and -1. We're only going to look at this piece of the sine curve. That's all we're going to consider. Now, it's interesting. No one ever sat down and held a meeting and say, okay, we're just going to look at this part. That's just what's been done over history, traditional. So now this function, if I try to draw a horizontal line, I'll only intersect the curve in one place. So this function is now 1-to-1. That means it has an inverse. So we say y equals the inverse sine of x means the same thing as the sine of y equals x. It's very much the same kind of trick as we did with logarithms. Now, what's going to be the domain and range? Well, we know when we do an inverse, x and y swap. So in this situation, x is going to be between -1 and 1, and y is going to be between minus pi over 2 and pi over 2. So that's why on your calculator, when you hit the inverse sine function, remember, if you hit this button on the calculator, and say you have your calculator set in degrees, if you type in the inverse sine of 1/2, your calculator will give you 30 degrees if you've got it set in degrees. Here's why. If we translate this domain and range for the inverse sine function, you're only going to get these angles. Remember, y here goes from minus pi over 2 to pi over 2, and y is equal to this, and all inverse trig functions are angles. Your calculator will only give you angles as answers in quadrants 1 and 4. It has to do that. In fact, as I've stated in class, or will state in class, this is how I remember this. This is how I remember the domain and range, focusing on the y. Focusing on the y, this tells me that the angles have to be between minus pi over 2 and pi over 2. Now, a similar thing is done for the cosine. Y is equal to inverse cosine of x. And we do a similar thing for the cosine function. We restrict the domain if and only if the cosine function equals x. These are the same thing. And for the cosine function, we use the top half of the circle. So that means x again is going to be between minus 1 and 1. And now the angles I've got shaded here, the angles are between 0 and pi. So that means if you use the inverse cosine button on your calculator, it has to give you an angle in quadrants 1 and 2. It cannot give you an angle that's in quadrants 3 and 4. You have to be aware of that, or you're dangerous. And finally, what we do for the tangent function, we take what a lot of books call the principal branch. Now I'm drawing the tangent function, and I'm drawing what's called the principal branch between minus pi over 2 and pi over 2. And remember, the graph of the tangent looks like this. Now let's just make some observations. As x goes to pi over 2, as x goes this way, y goes to infinity. And as x approaches pi over 2 here, minus pi over 2, y goes to minus infinity. Okay, now remember that. We need that. The only point they share in common is 0, 0. So here, I'm taking just the principal branch. This is called the principal branch. If I took other branches, it would not be 1 to 1. So for the tangent, inverse tangent, we say y equals inverse tangent of x. That means the same thing as the tangent of y equals x. So over here for the tangent function, our domain goes from minus pi over 2 to plus pi over 2, but it doesn't include pi over 2. So that means over here that the angles, remember this is an angle, the angle is going to be minus pi over 2 to pi over 2. That's the angles I've got. See, the x values here are going to be the y values here. Well, what do the y values do? They go from minus infinity to plus infinity. So x can be any real number. Okay? Now, this one appears a lot. It's got an interesting graph. I want to graph this one. We'll graph the others in class, but I want to graph this one. See, in the tangent function, you have vertical asymptotes. So that means for the inverse tangent, you've got to have horizontal asymptotes. So this vertical asymptote is x equals pi over 2. So for the inverse, it's going to be y equals pi over 2. Down here, you'll have y equals minus pi over 2. Now they share 0. And what you want to do in these two cases is swap x and y. And what you'll do is you'll get this. And this function right here appears in the calculus courses much, much more than it should have. Much, much more than these other two. Now, these other two do appear, but this one in problems in calculus, the inverse tangent function appears over and over and over, much more often than the other two. So let's look at some problems in the worksheet. And again, for the inverse sine function, this would be the domain, and this would be the range. And similarly down here, this is going to be the domain, and this would be the range. So in the worksheet, I'm not even going to do this top half because I've just sketched them. Now, I did sketch this one. I did not sketch this one and this one. I'll do those in class, or you can check the answer sheets. Let's go on down and look at some of these problems. Now, you've got to be careful. You've got to be so careful. Part A here is an inverse cosine. Remember, this is an angle. Well, the inverse cosines can only be those angles. So see, this is really asking you a question. And the question is, what angle in quadrant 1 and quadrant 2, what angle has a cosine of square root of 3 over 2? Well, that's going to be pi over 6, because the cosine of pi over 6 is the square root of 3 over 2. Remember, that's an angle. Let's look at B. It's the inverse sine function. I always do this. I do this every time. And in fact, everyone else I know who teaches this stuff does this. Now, I want the inverse sine of -1. What angle has a sine of -1? You got it. It's minus pi over 2. See that? Now, inverse cotangent of -1. What angle has a cotangent of -1? What angle has a cotangent of -1? Well, let's think about it. That would be cosine over sine. For the cotangent to be 1 or -1, it has to be some multiple of pi over 4, doesn't it? Okay. Well, now let's think about it. Let's look at the principal branch of the cotangent function. That's pi. That's pi over 2, and it looks like this. So the angles go from 0 to pi. Okay? So that means for this, the angles have to go from 0 to pi. So that must be 3 pi over 4. Okay, now here's some cool problems. Look at G. We would love for those to cancel. But for those to cancel, this has to make sense. This has to make sense. So, cover the cosine up and answer this question. What angle has a cosine of minus square root of 2 over 2? Well, for the cosine function, the inverse cosine function, again, I'm covering up this. Just cover that up. And look at this inner part. Cover it up. What angle has a cosine of minus square root of 2 over 2? Well, it's going to be the multiple of pi over 4. But remember, the inverse cosine only makes sense from 0 to pi. So what angle has a cosine of minus square root of 2 over 2? It would have to be this angle. So it has to be the multiple of pi over 4 in quadrant 2. Well, here's pi, which is 4 pi over 4. If we back up 1, this is going to be the cosine of what? 3 pi over 4. So exactly, these in this case, they just cancel. So you get a minus square root of 2 over 2. Okay? So the long and short of it is, now I'm going to go back to this other page. When you have this, when you have cosine, inverse cosine of A, the question is, when do these cancel? Well, look, these are going to cancel when this A is between -1 and +1. When that number is between -1 and +1, they will always cancel. Look back at our picture. Let me erase this. These are going to cancel if this number is between +1 and -1. Well, the square root of 2 over 2 is approximately 0.707. So negative 0.707 is definitely between 1 and -1. So these cancel. So on an exam, these will cancel. These will cancel if this number is between 1 and -1. Okay, let's go over here. Now, when did these cancel? Well, see, if we did cancel them, let's just pretend we could, you would get 4 pi over 3. Well, see, that's not going to be possible, is it? Because the domain of the inverse sine function goes from minus pi over 2 to plus pi over 2. You see? And 4 pi over 3, 4 pi over 3 is in this quadrant. This angle, 4 pi over 3, is not in the domain of this one. So they don't cancel. So here's what you have to do. When this happens, you just cover this up. What is the sine of 4 pi over 3? Well, it's going to be the same as the sine of pi over 3, but in quadrant 3. So the sine of 4 pi over 3 is going to be a minus square root of 3 over 2. And now we want the inverse sine of this. So if this angle here is not between minus pi over 2 and plus pi over 2, if this angle is not between minus pi over 2 plus pi over 2, you cover this up and figure out what this is. It was minus square root of 3 over 2. And now take the inverse sine. Well, remember, this is an angle. And the answer to this question is going to be in quadrant 4 or quadrant 1. So what angle has a sine of minus square root of 3 over 2? It's going to be the multiple of pi over 3 here. So this is going to be minus pi over 3. Okay. That's kind of fun. Let's go over here and do k. I want the inverse cosine sine of pi over 6. We'll just cover this up. What's the sine of pi over 6? Well, that's a half. So I want the inverse cosine of 1/2. Now remember, it's the inverse cosine. So it's got to be the angles between 0 and pi. What angle has a cosine of a half? Well, that's pi over 3. Let's do n. Let's do n. So we cover this up. What is the inverse cosine of negative square root of 3 over 2? Well, remember, that is an angle. What angle has a cosine of minus square root of 3 over 2? Well, it's negative, so it's got to be in this quadrant because the cosines are negative over here. And the angle that has a cosine of minus square root of 3 over 2 is going to be the multiple of the reference angle pi over 6. The cosine of pi over 6 is square root of 3 over 2. So I'm looking for the multiple of pi over 6 in quadrant 2. So this is pi. So I need 6 pi over 6. Back up 1. That's going to be 5 pi over 6. So I need the sine of 5 pi over 6. And that's just a half. The reference angle would be pi over 6. The sine of pi over 6 is a half. And in quadrant 2, the y values are positive. let's go over here and do n, and that'll be the last one. So what's the inverse tangent sine of pi over 2? Well, the sine of pi over 2 is minus 1. So this would be the inverse tangent of minus 1. Now remember, it's the inverse tangent. So I'm dealing with the angles from minus pi over 2 to plus pi over 2, not including the endpoints. So this is a question: what angle has a tangent of minus 1? Okay, well, the signs have to be different. So it's going to be the multiple of pi over 4 in this quadrant. So it's going to be minus pi over 4. Okay, and that'll do it for 5.5, and that will do it for Chapter 5.